start with the introduction on PyCOMPSs. So the motivation, you know that when we talk about distributed computing in general with high performance computing, we deal with constantly with new complex architecture that comes every day. So each one of these architecture has its own programming API, its own way of usage. So usually a developer has to adapt his work to the different programming models behind this architecture. For example, to use GPUs or non-volatile memories, you have to use the specific API provided by the architecture itself. Also, the user can deal with the two different paradigms: the fine grain, let's say the how to execute and program application for this kind of architecture, where you have to use the in-memory of the CPU, or on the other side, you have to execute the application, the code, on a coarse grain, in a coarse grain way, where you have to deploy the code on clouds or clusters. So you can see that here we deal with different kind of issues, both on accessing this infrastructure and using programming the infrastructure. So the point here, how we can help the programmers to reduce the learning curve, to access and to use to these platforms. And above all, what about non-computer scientists? So here, I guess there are many of you are not directly computer scientists. You are just users, that you have your scientific problem, and you don't want or you don't have the experience to deal with this technical problem of accessing a specific computing platform. When again, other problems, how once I manage to access a platform, so once I manage to execute my code on this platform, then how can I improve this execution on the specific architecture? How can improve the efficiency? How can improve the speed of the execution of the application? When I'm using cloud, should I go for a shorter, let's say, time application, but paying less for the cloud resources, or going for more efficient resources, or paying more and having more efficient usage of the platform? So in the end, what we try to deal with in our work is to help the user to port the application, to make the application more efficient on a quite wide set of architecture. In this picture, we represent also what is very common now: the fact that we have to deal with the resources that belongs to the so-called edge. I don't know if you know this word. Edge is called that part of a computing infrastructure where very close where the data is produced. So we can think about a sensor in a car, in an autonomous car, or also in our mobile phone. We have a lot of information that is produced and consumed by other applications. Think about fitness applications or maps, etc. These resources, in the end, are not. You are not ensured that they exist always in your computing network. So we have to deal with this dynamicity of availability of the resources. Again, in the same deployment, we have heterogeneity of resources. You can see in this picture we have a small device like a Raspberry with its own architecture, but then you can move the computation to a laptop, so another architecture, or to an HPC cluster as Mare Nostrum. So crossing different types of network in stable connections across the devices, different policies of trust and security, And of course, why not? When you talk about mobility, one of the issues is the power. We call this this picture, what we represent is so-called computing continuum. So something continuum in the sense that the same application is deployed and the execution is spun across a quite different set of resources with the problems that I described now. So what is the idea? So the idea is to create tools, again, our final motivation, tools that make developers' life easier. So let scientists or users in general focus on their own problem, so on the scientific problem, not on the computational side of the problem. In this way, what we do is to provide an intermediate layer, okay, that acts on behalf of the user and takes the work of the produced by the application and deals with the distributing the work, dealing with all the different architecture that we can find in the deployment of an application, and also to improve the performance of the application on these resources. On top of this, we provide, as you will see, additional tools to monitor the execution of your code, and so you can monitor through a graphical interface. You will see you can monitor the execution in real time. Okay, you can see what's happening, and we also are integrated with other performance analysis tools, also developed here at BSc, to analyze post-mortem, as we say, the performance of the execution of the application. This way, as I said before, it's not just executing something, it's just improving above all the efficiency and the performance of the application on a given platform. Another thing, as you will see later in the session by Rosa, we are, of course, now dealing a lot with the integration of the classic, let's say, workloads, classic application with machine learning and data analytics tool. So more and more now we deal with applications that need the integration of artificial intelligence and machine learning algorithm, for example. So in this picture, we represent this, our vision. So as I said, the idea is that the user provides her own application, and they don't have to deal with the gory details of each API to access the computation infrastructure. So the applications are developed once, and then we have the programming model level, which provide a quite simple abstract interface to the user, to then let the application be managed at the execution time by the runtime, which is the core of our programming framework. And this runtime then is developed in such a way that he can talk to Mare Nostrum, to a specific cloud. So if you want to execute part of the application on Amazon or on Google Cloud, we can support this, or it can be executed in a generic computing infrastructure. So in this way, we aim at having the programming logic independent of the computing platform. This is a quite important part of our work. It's important to say that once you program your application with the COMPSs or PyCOMPSs, you don't have to adapt your application to be executed on Mare Nostrum, on a supercomputer, or in the cloud. It's just a matter of configuring the runtime to let him talk to the specific computing backend. Just for your information, let's say what we do with COMPSs dates back to, you can say, 20 years ago. when BSc started the work, the research on the programming models. So COMPSs belongs to a family of programming models developed here at BSc called star superscalar. The other important programming model here is COMPSs, superscalar. But here you can see this picture. We represent the different targets, let's say, of the of architecture and also applications that can be programmed with the two models. With the COMPSs, we deal with more coarse-grained platforms and application where tasks are the task granularity is about going from milliseconds to days of execution. We are not talking about applications, but tasks of the application. And these tasks, this application run on nodes of a cluster. For us, also a cluster, Mare Nostrum is a distributed platform because we treat the nodes of the supercomputer as an independent node, or node of a grid, of a cloud, of a container cluster, etc. And the file and the dependencies between tasks in COMPSs are files or objects, and we deal with Java and above all now Python application. So with COMPSs, we stay on the distributed side of the programming model. So we distribute the task on this platform, while OMPS is more on quite lower task granularity. We're talking about microseconds, each task lasts micro or milliseconds. The dependencies are not files or objects to be shared across the nodes, but the dependencies are in the same memory address space, and applications are mostly C, C++, and Fortran. But the main idea of the task-based programming model is shared, it's the same. When I talked here about task, so what is a task in when we program with COMPSs? The idea of COMPSs, as said before, is that you don't have to learn a new programming model, a new programming language. The idea is that the code of the user still is sequential. So you don't have to think, let's say, in or using as when you use MPI. Okay. The idea is that you use your general compose programming language as Python or Java, and we annotate the code to identify the part of the code that can be a task. And we this annotation are hints to the runtime, okay, to then execute those part of the code as a task on a set of resources. So a task, when we talk about task-based programming model, a task is the unit of work of COMPSs. When we annotate the code of an application, then these annotations are intercepted, are read by the runtime that builds a task graph. Here we have in this picture, you have an example of what is a task graph. So a task graph is represents what happens at runtime, where you have the dots, which are the functions that we identified as a task, with the directionality of the data. So the data is represented by the lines here, the arrows. So in this case, we have a dependency graph. Dependency because here these executions have dependencies between each other. So we are here building a workflow. Okay, you don't have to build explicitly the workflow. The workflow is implicit again, so it's built at runtime by COMPSs, and as you can see, through this implicit build of the workflow, we exploit the parallelism. Because here you can see, as we'll see then with examples in the code, the idea is of COMPSs is to parallelize not through a magic in in the runtime, but through this detection of the dependencies between the data. So tasks that are dependent between each other, for example, these green dots here, can be executed in parallel. Okay, then they have other dependencies before and after, but you have to think about that this code in principle is sequential, but through the identification of the task and the directionality of the data, the COMPSs runtime is able to exploit the parallelism in the execution. And again, the important thing is that this graph is not specific of an application, of a platform. So this is the execution graph of this application, okay, through COMPSs, and this is independent of the platform. Other types of parallelism that you can have with you can introduce with COMPSs. As I said, in general, we have the tasks in COMPSs are coarse-grained. As I said, are tasks that last seconds or minutes or hours, okay, on a node. But you can have also a task that internally is a type of fine-grained task. For example, you can have threaded task internally. A task can open different threads, thus exploiting the internal resources of a CPU. You can have MPI application, as you will see tomorrow. You can integrate in the COMPSs programming model. You can integrate tasks that are internally are MPI. What is the benefit? The benefit is that you don't have to deal with the allocation of resources. So inside the same application, you can have parts of this application that are allocated in Mare Nostrum, for example, but inside the same execution. So it's up to COMPSs to reserve the proper number of resources on the cluster, and the proper time execute those MPI tasks. Of course, we have the integration with DOMs. So in the family, we are integrated. So you can build application that has two levels of parallelism, coarse-grained parallelism with COMPSs, internal task parallelized with DOMs. And also we support streaming. So to support data flow execution. So it means that a task is living as long as there are input data that are streamed. Okay, in this way you can have tasks that are classic tasks that receive an input, execute something, produces an output, and then end. And you can have at the same time tasks that are always on, waiting for a task streamed through Kafka, for example. As I said before, you can introduce in your application the concept of failure management. In this way, this is very useful because when you have, for example, long-lasting application, you can have part of this application that can fail. And of course, in the classic execution, let's say, all the application, all the execution will end, will fail. Through this failure management, you can decide which part of the code can fail without letting fail all the application. So you can control the overall execution of your code to decide, for example, that if you have different pipelines executed in parallel, you can decide that if one of those pipeline fails, it's okay for you. Okay, you can still have you can still get the results of the rest of the application, or you can decide that not. You want to end all the application. You can decide to to retry the execution of the failed task, etc. So other advanced features, as I said before, we have a parallel machine learning library, this lib, which provide already available algorithms parallelized with COMPSs. So you don't have to program the code to be parallelized by COMPSs. It's already available through a library, as you will see later. It's very easy. As you know, scikit-learn So we are based on the same concept of scikit-learn, but through a distributed array, as we'll see later. We parallelize scikit-learn somehow. And the important thing is you have just to import the library and train the model using your data and have also predictions. So we, I mean, this is just few resources where COMPSs is available, as we say, in production. For example, in Mare Nostrum, COMPSs is available for you, and it's always updated to the last version. It's available also in other supercomputing computers in Europe through the participation in several projects. Okay, we had to test COMPSs in other supercomputers, and this is available there. We used a lot in the EGI Federated Cloud. EGI is a European network of cloud providers for science. And also in the States is available, for example, the Chameleon Cloud, which is another scientific supercomputing network. So this is just a picture to say that you have your code written in Python, C, C++, Java, whatever, and then your application is enacted by the COMPSs runtime on quite a wide set of resources. As Docker, of course, now we are working a lot with containerization. So you can, as you will see, we can use easily COMPSs in containers platforms. This is a bit more detailed, but also a summary, of everything. So here is a flow of the development and execution of a COMPSs application. So you have your code, which is sequential. Okay, you annotate the code in Python or Java, and this code, independently if it's Python or these are internals. Okay, this code is then treated by the COMPSs runtime. You will see from your side as user, you will see your code executed sequentially. Okay, you don't see any difference in the execution of the main program. But internally, what is happening that COMPSs is analyzing that code, the parts that are annotated, of course, and is building a task dependency graph, as we said before. And these tasks are scheduled based on resource availability and data availability, of course, is scheduled on a different set of resources. So your code, onto the code, becomes a task, and these tasks are executed on the nodes of your computing platform. And of course, it is the runtime that doesn't just execute, but also takes care of the dependencies, also in terms of movement of the data. Okay, so if the data are files, these files are moved. If are objects, those objects are serialized and moved across the nodes, etc. Today you will also use, as I said before, there are several additional tools that we provide to help the analysis of the execution of the code. We have a monitoring tool that lets you see what's going on in real time during the execution of the application. We have the integration with Jupyter. You will use later, okay, during the tutorial. So this lets you execute interactively Python code using the power graphic of Jupyter. And as I said before, what is very important for us is to provide the way for you to analyze in a powerful way the behavior of the application through traces. So you will see also what is a trace. Trace represents the with very detail what's happening in the execution of the application. So through this analysis, you can see how the execution is balanced or not. So how your code is written, you can see if there are problems in the scheduling of the task, etc. So it's a very powerful tool to improve the performance and efficiency of the application. As a final picture, with COMPSs, we try to enable we try to, first of all, try to ease the life of the application developers, providing a workflow environment that not just allow to parallelize the execution of the application, but also provide advanced features as the integration of HPC simulation with data analytics and the machine learning through this leap. And we support a dynamic workflow that can change the behavior during the execution through, for example, the failure management. We support different data management tools, including data streams. In this way, we enable the execution of application composed of classic task-based function, but also with data flows in the same application. We are integrated with other tools developed here at BSc for persistent storage as DataClay Cuba. That goes beyond the traditional file system, and we transparently let you execute the application on different computing platform across HPC clusters, Docker or containerized platforms, and executing on all the, what I said, the computing continuum, going across the edge devices to cloud and to supercomputers. It's important to say that our work is based on the research and developments that we do every day on different projects, European projects, where we develop new features or we implement a new application using existing new features. An important project now is eFlows for HPC, coordinated by Rosa, by our group, and that's it. So these are several projects that are mainly all the projects that we are working now. We work, for example, I don't know, someone of you coming from the life science department here at BSc, we are in the BioXcel Center of Excellence, where we develop quite advanced workflows for molecular dynamics. And this is the actual status of our, I think I didn't forget anyone. I don't know, because our graph is quite dynamically, quite dynamic recently, but anyway, this is our group. So